Hey guys! So this will be a step-by-step guide on how to flash a custom firmware on these e-paper price tags and how to communicate with them via this USB Zigbee stick, which contains a CC2531 microcontroller. In addition to it, there is a Python script to drive everything. Hey Aaron from yesterday, maybe you should tell people what they are able to do with this 40 minutes long video. So what this is all about: you have some old e-paper price tags that you want to reuse and control them via a Zigbee stick like this one. You can flash everything with an ESP32, and in the end you can assign different Macs to your e-paper displays and display graphic contents on them sent from the PC or a Raspberry Pi, etc. It wasn't that hard, right? The custom firmware flashed on them is from Dmitrys, and it's modified a bit to work with them a little bit better. And the station code right now is from Daniel Kusera. I want to show you really step by step from 0 to 100 how to get it running, as right now it's quite complicated. In the GitHub repository you can find link down below. So you have really a manual on how to solder the flashing pins on the e-paper price tags and how to also flash the correct firmware onto this Zigbee USB stick. This involves a little bit of soldering, a little bit of Arduino programming, and also a little bit of 3D printing to have it simpler to flash many of these price tags at once. As you can see, here are quite a lot, and soldering pins to each of them is quite some work. So yeah, I created this flashing jig which uses Pogo pins, and I just want to show it to you a little bit on how it's intended. You don't need to use it if you just want to flash a few. And yeah, so let's start with it. I will do it step by step and start with the USB CC2531 Zigbee stick, how to get the firmware onto it. As a quick reminder to mention, this manual could be outdated in the future, so please check any notes down below or at the GitHub repo about any new firmware version or new method to update these displays, as this is just the state right now and there's active development going on. So we want to start with the CC2531 USB Zigbee stick. For that we will use an Arduino, in this case an ESP32, but it could be any board which runs on 3.3 volt, as the CC also uses 3.3 volt. This works without any soldering if you got this connector with your CC USB stick. Most likely it is with it, otherwise you need to solder or somehow otherwise connect to this debug header. We will now use this adapter board and then some Dupont wires to bridge it to the Arduino. There are no additional parts needed, everything else is in software. Here we got the pin out of the debug header. You can see here that, just to show it as well, we have this 10 pin header and the pin 1 is here on top, and you can also see here pin 1 is being used. What we need is ground, target voltage, DD, DC and reset. So it's just these 5 wires. And when we look at this adapter, we need of course to plug the wet side into the 1, and on the CC board as well into the 1, like that. And the second connector can be removed then. And here we have again this 10 pin connection, and we can bridge it to the ESP32. Which pin goes where needs to be looked into the software, and that's the part where we will look into now. To get started with the software, you want to download the so-called CBS Flasher repository. You can just click on download zip and download it to your desktop best. This will include everything already for the custom firmware of the ePaper price tag, but also the firmware we want to flash onto the CC USB stick. The other repo you want to clone is the so-called cc.flash repository. This includes the Arduino code for the CC flasher and also a Windows application for it. After the download, we can extract both of these files. After that is done, we can start or go into the cc_flash folder and start this .ino file, which will then be used to flash the ESP in my case with the Arduino code, which allows to act as an interface to the CC. Here we can directly see all the pins that are used for the ESP32 in my case. I have the DC pin on 19, the DD pin on 23 and the reset pin on 33. If we look into or at the ESP32 board, we can see these pins here, and we will then just bridge them over to the adapter or directly to the CC USB stick. This does not include the ground and 3.3 volt rail. We need to bridge that as well, of course. So I will now take 5 Dupont wires and bridge them accordingly to the manual. So we have the ground pin and we bridge it on the Arduino. This is, by the way, a Lolin 32 light board. It's quite cheap, but also has some limits, less pins and some other things, but not so important. We will bridge the target voltage sense. Here it is important that you can see that there are two pins which are marked voltage or 3.3 volt and target voltage. And here is a bridge on the adapter board which we need to close for it to work. Otherwise the board will not be powered. If you do not have anything to bridge it, you can also just use the USB plug and stick it in the PC. That way you could leave out ground and 3.3 volt, but it's better to also bridge it. So I will now also connect the 3 volt line and then the data lines, which is here the DD line on pin 4, and on the PC it is 23 for this source code. Then the next pin is pin 19, which is DC. So I will bridge that, and then also the reset pin, which is pin 7. That goes to 33 on this board, like so. And this is basically it. I will now also bridge the power supply rail. So this is now bridged. Yes, it's soldered, and I told you it would work without soldering, but you can just put any wire inside of it and just bend it around to bridge it that way. Now we can connect the ESP32 to the computer, which should show it up as a UART device, and we can see here now we have a new COM port, and I can simply click on upload to flash this ESP32 with the interface software. So to get this to work, I'm expecting you to have installed the Arduino IDE and also the ESP32 libraries, of course, but that is depending on the flashing board you want to use. So the upload has now finished. We can close the Arduino IDE for now and go back into the CC flash repository, and we have the cc.flash exe, which is the software used to connect to the ESP32 to then flash the CC USB stick. It need the .NET software. So the .NET framework was now installed by Windows automatically. And on the next start we should see the interface already. And that looks pretty good. There you also need to select the correct COM port and you can click on connect. And if everything is correctly connected on the ESP32 side and the firmware is correctly flashed, it will successfully detect the CC2531 stick. You can now select the firmware we want to write. This is a TI Mac Zigbee stack, and this is included in the ZBS Flasher repository under the CC2531 station folder, and there we have this bin file. To flash it, we now just simply click on write. This will take a few seconds, so this should be ready any moment, and you can see it took 56 seconds, but from the CC part this should be it already. So we can now disconnect the CC USB stick and also can try to connect it to the PC now, as it should enumerate as a COM port as well. So after I plugged it in, you heard that it was detected. And if we now open the CC Flash software again, it should show a different COM port, and as we can see we have a new COM port which is COM port 15. So that means the flashing was correct and the TI Mac stack is now successfully running on the CC's USB stick. We can disconnect the DuPont wires from the ESP32 as we needed to flash the displays now. We now continue with the e-paper displays. In this case it is a 2.9-inch version. There are also different versions around. Especially on these two types, the PCB inside of them is likely the same. Just on one it's cut here. This is important as we want to access the flashing pins that you can see here on the back side. You can access them by opening the battery case. This works the same way on the smaller ones. And if you flash a lot of them, it's advised to use such a Pogo flasher. There, these Pogo pins are spaced and positioned as needed for the flashing adapter. So you just can insert it, hold it by this cover, and an ESP32 board is again here on the bottom, which will interact with the PC, with the flashing software, to flash the firmware onto it. If you only want to flash one or two of these, printing such a jig is maybe too much, then you can also directly solder onto these pins inside and connect it to an ESP32. I will open one up. I'm using my fingernails for it. These are just always with you. To do so, we have this part here where the antenna is sticking a bit to the outside, and that makes it a little bit more easy to open it up, as you can see them poking out here a little bit. Trying to do it here, it's not so easy. This just showed that it is the simplest way. You can then just go around with a screwdriver or X-Acto knife, etc., or your fingernails of course, and pry it apart, so you will end up with the different parts of the display and case and so on. And of course it's now not working as it used to, but we will get there. So here we go. So, like so. We have the top part, the bottom part, and the PCB, which also contains or is glued together with the e-paper display. Here we then again have these 10 pins, and we want to connect to a few of them. I got the pin out ready here. You can see for once it here printed out on the paper, just to have it readable. This is also available on the GitHub repository, so you don't need to print it out or look out for this video. And then also I got here the pins where we want to connect to the ESP32. I will not show it now how to solder it. If I personally only solder 1 or 2 to an ESP32, I'm using such a mild copper wire. It's really, I cannot live without it. It's called in Germany Kupferlackdraht. It's like, I think also in motor windings and such, as this will not conduct like this, as there is a thin layer of isolation, and only if you burn it away via the soldering iron, you have it conducting to the points where you want it. As an example, I will continue with this contraption, as it's the best to show that way. You have for once the display here, again via Pogo pins connected to the flashing pins. And on the lower side you see how it looks. It's just these emild copper wires connected to the Pogo pins. On these Pogo pins you need to be very careful to not heat them up too much, not only because of the 3D printed jig, but also because the spring inside of them tends to get brittle and not work that well anymore. This is connected to the ESP32 exactly as the pins here suggest. It is very important that the power of the microcontroller in the displays, or the main power of the display itself, is not directly connected to a GPIO of the ESP32. Instead, it is switched to a 3.3 volt rail, as this can draw quite a lot on startup and it could destroy a GPIO on the ESP32. You can connect multiple GPIOs together, that way it can work, and it did work in the past, but it is advised not to do it. Personally, I'm using such a 3.3 volt LDO for it, which I got from LCSC. It is TSOP25, I think. One is laying now here. And as many ESP32 boards also got such a voltage converter, as you can see here, where you have the 5 volt rail you want, and the ground and so on. So I'm soldering these other 5 pin bodies onto it, like you can see here. But I do not solder on the enable pin, and of course also not the voltage out pin. The voltage out pin is then going to the display, as you would expect, and the enable pin is going to the GPIO 16 you saw here from the ESP32. And that way you can switch on and off the power of the display. And the reason for this power on and off switching is that you cannot get the display out of the debug mode without toggling the power supply. You could also just remove the display and put it back in. That way you don't need any LDO or transistor to switch the power supply, and can just connect the power to the display all the time. Flashing will still work then. This all looks quite like a mess now. So let's continue with the jig. Here, as mentioned, inside is the ESP32 board, also connected to the Pogo pins. I additionally added here an LED but you do not need to look out for that. We want to flash the ZBS flasher software now onto the ESP32 of this board. To show it, I will go back to the PC, and of course I will also insert one display already so we can see how it looks in a moment when it's being flashed. To get the display part flashing running, we do need the Visual Studio Code software and also Platform IO being flashed or installed inside of Visual Studio Code. You can search in the internet for many manuals, so you get that running. You want to add the ZBS flasher folder called ESP32 flasher into the Visual Studio Code environment. And to do so, we open up the, or pull the folder into the Visual Studio Code Project Explorer, and it will be searched by Platform IO and can then be compiled. To get a bit into the source code of it, we here again have the pinout of the ESP32 which is used. You can select any pin here as well, especially on an ESP32. If you do use another Arduino board like an ESP8266 or such, you need to look out for the correct pinout, of course. So after Platform IO has initialized everything correctly, we want to select the correct COM port in the platform INI. For that I'm reconnecting now the flashing adapter. I know that it was the COM5 if I remember correctly. And after that we can here click on upload, and this will compile and upload the code onto the flasher, which I will do now. This could take a while on first start, as it will maybe download a few more things for the ESP32. So after we waited until a successful upload of the ESP32 ZBS flasher firmware, and of course reselecting the correct COM port, we can take a look into the ZBS flasher PC side software, which is this zbsflasher.exe. If you want to run it on Linux, you can use this Python script, but we will use the precompiled one. So to use it, we need a terminal, and we open one via entering command here in this top folder section. If we now let the ZBS flasher run without any arguments, we will see that it spits out a little bit of a manual on how to use it and also the available ports. So to flash now a firmware, we want to use it as intended and use again the ZBS flasher, COM port 16. We want to write into the flash, and we also want to write the firmware that is inside of the custom firmware folder, which is a pre-compiled custom firmware. You could also compile it on your own via this folder, but I will not go into it right now. Normally you just have to open this, make it, or this compile.bat, and it will compile the firmware for you, but that's a different topic. So to use this firmware, we enter the folder and also enter the firmware name we want to flash. In this case I'm using the version 1.8, and it is only for the 2.9 inch version of the display, which we have connected here. After I now press enter, it will try to talk with the ESP32, as you can see, and it will already, or it is already flashing the firmware onto the display. We can now see that the display is refreshing. This will show that we have only an FFF MAC address here on the top in a moment, like you can see here. The reason is we want to set an own MAC address into the info page. This info page is like an EEPROM on an Arduino. To do that, we again use the ZBS flasher, use COM16, and we first want to read the info page by read I, because in that info page there is some calibration data that should not be lost. So we will read I and just read it into the so-called dump bin. It will then again talk to the display, and we should see a new file here, as you can see. And we now need to edit this file. I'm using the so-called HXD editor. It's a hex editor and quite powerful for Windows. We can see here that there are mostly FFFs, but the first line consists of this calibration data we do not want to lose. To set a MAC address, we can now use these first 8 bytes of the hex 10 offset and set something custom we want. I will now just enter 1, 2, 3, 4, 5 and save the file again. Now this is the content of this file, and we want to flash it again into the display. To do so, we use the same command, just write I. This will now flash it into the display, and you may have noticed now that there is no change on the display at all. This is because the display saves in its external flash that it has already written this config or this start window. So it will not redraw it even if we now have a different MAC address. So it is advised to first write this info page to have a correct MAC address in the region, and then flash the main firmware. I will redo it now with a different display to show that as well. So I will reinsert a new display and we'll just redump the info page like so. It will now appear here again, and I will just save it as 12FF and will rewrite the info page again. So we now have set the MAC address first and can then flash the firmware itself. So in a moment it will boot again, but with a correct MAC set, if we first write into the info page and then into the main firmware. So you can see now that we have all Fs but 1, 2 at the end. This is because the direction of the MAC address is just the other way around, but that's no big hassle. So we see that a MAC address is now correctly shown, and this is basically it. Everything for the display itself. We can now reinsert the battery and everything will work from now on wirelessly, as we can see in a moment. So we can even disconnect the ESP32 flasher and can now continue with connecting these both via Zigbee and the station Python script. So after we now flashed the display with the custom firmware and also the CC USB stick with the TI Mac Zigbee stick, we can plug in the CC stick. We now want to download the ePaper station from Daniel. You can find a link to it via the station folder in the ZBS flasher, and there click on ePaper station. We then also want to download a zip file of it to your PC. Wait till the download is ready and extract it. and go into it. We see that we have 3 files here. We want to look into the station.py as we want to change a bit inside of it. For once we need to select the correct COM port. On Windows you can set it like this, on Linux the way it was before. Also we can see here that the script wants an image folder to put its temporary images. We need to create it as Python will not do it on its own. And it's also advised to change some settings when I found them again. Here. These are the settings the displays will get on first connection to the station, to the CC chip. For once we want to set, for me at least, the interval it will check in for a new image to 5 minutes. Per default it is at 15 minutes. And also for me at least, or it is advised to change the blank timeout to 0 and the associate timeout to 2. This means that if the display does not get a connection to the station 2 times in a row with this interval, it will disassociate from the station and it will be like factory default, and we will retries to get the settings on the next connection to the station. We want to save this, minimize it. The next part is we want to create an image we want to upload onto the display. It needs to be for the 2.9-inch display in vertical mode and 128 by 296 pixels, and I will just draw a little bit and save it into the folder. We have the Python script, so here, and it needs to be a PNG, and the file name now needs to be the MAC address in lowercase of the display this should be sent to. So in this case it's 14 times F, like that, and then 1, 2, and I will save it, and it will now be created here. After that we want to open up a terminal again via command, and now we can run the Python script via Python and station.py, and of course we need Python to be installed. We can start it. We will now see a lot of requests. This is because the e-paper wall is standing nearby, and don't be distracted by it. Per default, these displays will request every 15 minutes to connect to a station if they are in an unassociated state. And to bypass this timeout, I will now disconnect the batteries and short the battery terminals to fully discharge any capacitor, so it will really reboot. It is advised to not insert the batteries like this, one by one, and more to have them in the back plate and then close the back plate like that. This is because otherwise it could be that they will disconnect and reconnect fast, and that way maybe the microcontroller hangs. So if I now connect it, we will see that the display did request this image, the fff12.png, and try to convert it to the correct bitmap file to then upload it. But as we can see, there's an error. I think I did set the folder wrong, so I will exit the script via Ctrl+C. We'll open the terminal again and we'll correct my mistake like so, I think. No, let's do it that way. The first backslash was wrong. As it's for Linux, it will try to start at the very base file system, but we want to have it inside of the folder. So I will now restart the Python script. We'll reinsert the batteries to trigger a request again, like so. And we can now see on the PC that an upload is going and the display is requesting the image. After that, the image should be shown. As you can see, it will now refresh to that image. And now, after having a full refresh, it will boot every 5 minutes and ask for a new image on the PC. It will, on the next request, will not download the same image again as it has it already, and it is based on the change date of the image. So if we now, for once, open Paint already and restart or retrigger a request already, we can see that it did request an image, but it did not download anything. If we now want to trigger a new download of an image, we can just simply, for this example, write into the existing image and save it. So on the next checking in, the display requests the image version again. And if it's new, it will retry, or it will try to download that new image. As we can see now, it is happening. This could fail for some reason. It will then retry it in a few minutes later. Especially if there are many displays around that are talking at the same time, this could fail quite often. So you saw now the new image being updated. This of course brings you not very far to manual paint into this image, but this image could also be created by any other tool you have around, like another Python script that create this image or whatever you can think of, as this will completely run on its own and is not depending on anything else or the other way around. To now update the firmware of the display also over the air, we need to supply a firmware with, in this case, this name, also again into this folder, but it needs to have a higher version than the current firmware that is flashed onto the display. It will request it every time it checks in, and if there's a new firmware, it will update it. So that way we can even get a new firmware onto a display without needing to connect any wires to it again, or the flashing jig. And as you can see, if everything is set up correctly, it will work quite simple. And this is all just thanks to Dmitrys, which is the developer of the main part of the firmware and the reversing of this microcontroller that is inside of it. And it's just working so well. One thing I want to show it, especially on that firmware, if I now unplug the CC stick and trigger 2 times this check-in, like so, by reconnecting the battery, it will now save it that it has one time no connection to the base station, and then I will trigger it another time. And if it has now also no connection, it will show it by this line at the top, which will notify you about not being connected to a CC station. So this is used so you can even have the image here without a base station to be turned on. Otherwise the associate ready screen would come on again. This is special for this 1.8 or 1.7 version and yeah, is used that way. If we now replug in the CC stick, trigger a reboot, it will reassociate with the Python script it will then download that new image again and will refresh and of course show the don't show the line again, as we can see now. So that's it already. This is by basically just using these three parts, creating a Zigbee controlled graphic display, which just simply works. And yeah, in the end it's quite simple. The table is quite convoluted to get there where we want, but hey, if you got it running once, you can simply reflash a lot at once. Have a great day. See you next time and goodbye.